quick logistical things, and then we are going to jump in. First of all, hopefully you know or you're aware that homecoming the dance is this Saturday evening from 7 to 10. Just a friendly reminder, if you haven't heard before, or even if you have, that tickets are on sale before and after school and during lunch, Tuesday, Wednesday, Thursday, Friday. They're $5. No tickets will be sold at the dance. So if you think you're going to go to the dance, you need to make sure that you get a ticket before you leave school on Friday. Okay? If you would like to go to the dance, but $5 doesn't work in your budget, like that just doesn't work. And for some people, it's like, how could that not work? But let's be honest, for some people, that's an issue. And if that's true, and if you need some help, let me know, and I can get you in touch with the people that can get you a ticket. Okay? I don't want, and nobody in this building wants it to be a financial hardship for you not to be able to go to the dance. So $5. But if that doesn't work for you, let me know, and I can get you in touch with the right people. Okay? Today we're going to start with a warm-up problem. We're going to talk a little bit about standards, and then we're going to do some problem solving in a self-paced manner. So what I'd like for you to do right now is to take a look at this warm-up problem. You will need a whiteboard to answer the question, okay? So I'm going to put this up here for you to take a look at. Go ahead and get started, okay? What's going on? Okay, so let me walk you through kind of what we're looking at here. So it says, shown below are 6 velocity versus time graphs for toy robots traveling along a straight hallway. It says all of the graphs have the same time and velocity scales. So we're really just looking at the shape of the graph to figure out the magnitude of the displacement during the time interval. Okay, so we're looking at a velocity versus time graph, trying to figure out the displacement. Okay. Yesterday, we worked on those blue sheets. We started solving some problems. My friendly recommendation to you would be to look at question number 2 from the blue sheet. That's going to be the thing that's going to get you where you need to go. I want you to figure it out, and I don't want this to be me just telling you. So I'm going to give you a couple of minutes. I want you to process, think hard, do physics right now, okay? Go, go, go. Come on, Lauren. We can do this. It's going to be great. Okay. So we've got some uncertainty, but we've also got a lot of good brains in this room, and we've got a lot of good experience. I think we can get this. So let's figure out where to start. Does that sound okay? So before I even look, well, let me see your answers. Go ahead and put your answers up in the air, just so I can kind of write things down. All right, so I'm going to start writing, and then let me know if yours matches, and put your board down. So I see D, maybe, come on, is greater than, I couldn't see it. B equals C. What? I'm not saying it's right or wrong. I'm just saying I want to look at it. A equals E, greater than F. I see D is greater than B equals C, greater than, oh my gosh, seriously? Greater than A, greater than F, greater than E. Cool. E, greater than C equals B, greater than F, greater than D equals A. D, E, A, B, C, F, E, C, B, so we're doing at least F, the greatest or greatest to least? Greatest to least. All right, do I see more? Here we go. There's a sad face on there. That makes me sad. Oh, okay, good. We got this. It's going to be a beautiful day. All right, what else we got? Oh, B equals C. F, A, D. And you got one too? D, A, E, B, C, F. All right. We have a lot of answers. You might think, oh my gosh, well, we don't know what's going on. But to me, it tells me that there's a lot of stuff in there. If you look carefully, there's a lot of stuff that's similar. And so I don't want you to discount. I think we can do this. Let's take a step back I suggested that you look at the solving acceleration problems and look at question number 2, and it looked like this or something similar. I don't know if this was your period or whatever, but do you remember in number 2, we had the dog that was running 10 seconds, 5 meters per second. What's the dog's displacement? And we put this big thing in a big blue box or big blue thing. It says the area between the graph and the axis on a velocity versus time graph is the displacement. That is the key to answering this warm-up question. Okay? That is the key. If you don't know that,
what happens when it's triangular?
That's a great question, but it still says, and I'm glad you asked, it's still the area. It's still the area. It's just that the area looks different. So we'll talk about it. That's the whole point of doing this warm-up problem. So before we get to those weird triangles, let's do the ones that we understand. D looks a lot like the question that we did in question 2, doesn't it? It's got a positive velocity, a positive constant velocity. We can absolutely figure out the displacement of this object, right? This toy robot or whatever, right? So we're going to just look at that box, and it looks like it's just a nice little rectangle. It looks like this. We're going to find the area of that rectangle. We remember that the area of a rectangle is base times height or length times width. Do you guys have a preference of which I say? Is base times height? Okay, that's what I normally say. So I'll try and do it both ways. Base times height or length times width?
Times height.
Length times height, yes. Yeah, area of the base times height. Either way, whatever works for you. If it works in your brain, we're doing this thing times this thing. I'm just going to call everything 1 to make my life easy. So that's 5 seconds, 1.5 meters per second. So I've got an area of, hey, it was 5 seconds times 1.5 meters per second. And before I do that, let me just remind myself so that I don't forget that it's all about the units, isn't it? It's all about the units. So I've got meters per second times seconds. I've got a seconds on the bottom and a seconds on the top. What happens to those seconds? They go away, don't they? Which means that our answer is going to be in meters, which is what I want. So I've got something in meters. I've got 5 times 1.5. It's hard to see that 1, but it's there. 5 times 1.5 gives me something like 7.5. Is that right? Am I multiplying? Check my multiplication because sometimes it's not good. So that's 7.5 meters is my displacement. So far, so good. Yeah? Talk to me, Lauren. You got to let me know. Because if that doesn't make sense, then I want to back up further.
It's fine.
Okay, fantastic. Which other story of these 6 is kind of similar to D? A looks pretty similar, doesn't it? Yeah, it looks pretty similar. It's a little different, though. In D, the dog is walking in a positive direction. Life is good. It just keeps walking in a straight line. What's different in A? Which way is the dog going? Backwards in the negative direction. But he's also still walking at a constant speed. So let's take a look here at this one. So I've got a constant speed of 1 over those 5 seconds. So the area, again, is the base times height or the length times width. 5 times 1? What's that? 5. It's going to be 5 meters. Now, my delta x is actually, wait, it was -1, wasn't it? A velocity was -1. So the displacement, technically, if we're going to be good kids, is -5, isn't it? But is that the thing that I'm going to actually do my ranking with? No, I'm not. Why not? Magnitude. We talked about that yesterday. Remember, we said magnitude. It's the amount, the strength, right? So I'm going to write down here that this is really the answer I'm going to look for because I'm looking at magnitude is 5 meters. So I've got 5 meters here. I've got 7.5 meters here. I'm 1/3 of the way done. How are we doing? Are we okay? Issues or questions right now? Okay, so we can probably rank those, but let's see if these are any bigger or smaller. So now we're coming to this whole question of what happens if it's a triangle, right? I want to look at F. F is pretty straightforward. Describe the motion in F for me.
It's accelerating.
It's accelerating. Why do you say it's accelerating?
Because velocity goes up.
There's a change in velocity. Do you guys all see that? Yeah. So it's accelerating. It's accelerating positively, which means it's speeding up, right? Is it moving forward or backward? How do you know? The values of the velocity are positive, so that means it's going forward and it's speeding up as it does so. Okay? If I want to find the distance or the displacement that I have, we're going to do the same thing. It's the area under the curve again, but now the area, instead of being a rectangle, is a triangle. Friends, do you remember how to find an area of a triangle?
Nope.
If you don't remember, let me give you a cute little hint here. Look at this. It's just like this, except it's only how much of it? Half of it. That's all we're doing. No big deal. The area of a triangle is 1/2 the base times the height. Okay? The base is still 5. The height is 1. 5 times 1 is 5. Divided by 2 is 2.5. So the displacement here, delta x, is 2.5 meters. So that means that if I had this one over here, the one on A, let's make it positive just for kicks, and I have the one in F, and they're walking together, they start at the same moment, they start at the same place, which one's going to travel further? A or F? A travels further. It travels twice as far because it starts off going fast. So it's going fast, 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 fast the whole time. Whereas in F, it starts out slow and it gets faster. And by the end, they're going the same speed. They're going the same speed, but F started off a lot slower, so it's not going to make nearly as much displacement as A did. We doing okay so far? All right, so we got halfway there now. Now we got B and C. Are B and C similar in any way? They're pretty similar, aren't they? Are they different in any way?
Yes.
Yeah. Raise your hand for me if you can tell me a way that they are similar or a way that they're different. There are lots of ways, so tell me one.
C is like negative and it's going up, so it's like slowing down kind of. And
Yep.
so is B
Uh-huh.
because it's positive and it's going down.
Yeah. So in B, we're moving forward, right? We're moving forward and slowing down. We're going fast to slow. Moving forward. In C, we're moving fast to slow, but we're going backward. We're going the other way. Mel's looking at me like I'm a little nuts there. Talk to me. What did I say that was confusing? Do you want me to say it again? Would that be helpful?
How is it going from fast to slow in C if it's technically doing a slower velocity? Wouldn't it be going slow to fast?
That's a super, okay, I think I understand your question. I'm going to try and answer the question I think you're asking, but if it's not, then let me know, okay? So the initial velocity, come on, silly thing. The initial velocity here is 1.5, I'm going to call it, meters per second. Is that okay? The initial velocity here is negative 1.5 meters per second. Is that okay? When I'm talking about speed, though, all I care about is the absolute value, right? If I'm driving my car 30 miles per hour this direction or 30 miles per hour this direction, it's still 30 miles per hour. It's the same speed. Does that make sense? So they're both starting at the same speed. It's just that one's going this way, one's going this way. So for example, if you and I, I'm not going to make you do this, but if you and I stood up here and I acted out B and you acted out C, right? We're going to do the same motion, except you're going to go backwards. So I'm going to go fast and then I'm going to slow down. And you would go fast and slow down that way. Does that help a little bit? Awesome. Thank you for that question. How are we doing? Are we okay? Same motion in B and C, just moving in different directions. Same area under the curve in B and C, right? It's 1.5 times 5, 1.5 times 5 divided by 2. So it's half of the answer we had for D. If I do my math right, check me and make sure. I think that's 3.75 meters. Does that sound correct? Half of 7.5 is 3.75. Same here and here. The displacement in C is negative. Delta X would be negative 3.75. But again, all I care about is magnitude, so this is 3.75 as well. One more, but I want to check in. How are we doing? We okay so far? So far, so good? I've avoided E kind of actively on purpose. What's the story in E? It starts with a negative what? It starts with a negative velocity, which means it's moving backwards, right? And just like in C, it starts off with a negative velocity that's big, and then it slows down. Are you with me there? Okay, because it's going 1 meter per second, and then it's getting less and less and less and less. And how fast is it going right here? Zero. It has a velocity right here of 0. And then what's it doing? Then it's turning around. So here in the first 2 seconds, 2 and some seconds, it's moving backwards, slowing down, and then it's speeding up. Let me show you what that looks like, just to make sure it's working for you. So I'm going to start at the origin. I'm going to start moving quickly backwards. But as the time goes on, I'm going to what?
Come back to
I'm going to slow down, and I'm going to get to a stopping point, right? So let's do it. So I'm going to go fast, and then I'm going to slow down, and that's where that little blue line is. I've stopped, and then I'm going to go forward, and I'm going to speed up, speed up, speed up, and I'm going to get back exactly where I started. How do I know that? How do I know I'm getting back exactly where I started? Well, the slope stays the same, for sure. Also, if we take a look here, can I find the area of that little guy? Can I find the area of this one? How do the areas compare, friends? They are the same. So I have a little bit of a negative displacement. Negative delta x. And here I have a little bit of a positive displacement. And oh my gosh, a little negative plus a little positive gives me 0. So this one actually has a 0 displacement. Huh? It's like a light may have just turned on. Is that true? Yes! Woohoo! All right, really quick, double check. Do we have some success here? What's the biggest? What's the biggest? D is the biggest. Then what? A is the next. Then B and C. I had a lot of people that said that B and C were the same. Look at that. Look at all of your smartness. Look at this. There's a lot of people that saw that. I love that. That's fantastic. So even if you didn't know all the rest, like you got something out of that. All right. And then what happens after C? What's next? F. And then finally, E. E is the smallest. I have a few people that did tell me that E was the smallest. So good for you. I don't want you to feel like, wow, I totally messed that up. Wow, that was a really good opportunity to learn something, right? And hopefully, at this point now, you understand this. If not, you can watch this video again. We can just keep watching it over and over. Or come talk to me if you get stuck. B and C aren't equal? Why not?
They're slightly different.
They're pretty darn close to the same.
Yeah.
I think they're intended to be the same. If you measured it differently, you'd have to tell me why. Is that fair?
The B has like one box and then like just a smidge of the second.
Mm-hmm.
Where
I think they're pretty close. I understand what you're saying. Yeah. So if you put that on a test, because would this kind of thing be on a test? Could be. This would be like a totally reasonable test thing. So then, Lizzie, if you were going to say that you need to make it really clear that this wasn't 1.5, this was 1.6, and that this was 1.3, and that's why they're different. Does that make sense? And then I would be fine with it, and then I count it right. Is that okay? Awesome. Okay. We got to find out what's going on next. Holy cow. What do we got? All right. We're going to look at the standards here. So I mentioned as we were getting started that we have a quiz coming up, and indeed we do. These are the 3 standards that are up on the calendar on Canvas. These are the 3 standards that we have been working on for the last week or so. I want you to be aware that they are here and they exist. Okay? Standard, the first one says I can draw and interpret diagrams that represent motion of an object. We have been doing a lot of this, haven't we? We have been doing a lot of this. This is going to be a big one. The second one, we've been doing this kind of inside everything else, all of the conversations that we've been having. You know, I keep telling you to use the words. Use the words for physics, and that's what we're talking about here. Knowing what position, distance, displacement, speed, velocity, and acceleration are, and knowing the difference between them. So picking the right word for the right description. Okay? And then number 3 says, I can solve accelerating motion problems. We started that yesterday. We've been working on that kind of behind the scenes, but today is our really explicit we're going to do it day. So let me tell you the plan. Today is going to be a self-paced day. You are in control of your learning, okay? You need to do what's going to be best for you as you're learning this stuff, okay? I have recorded videos for a whole bunch of stuff. Please listen so that you know what's available, okay? The graphical approach to problems, that's the blue sheet that you already have out. We finished, I don't know, the front side or maybe part of the back, I don't remember. There are videos up for questions 4, 5, and 6. It only says 5 and 6 up there, but actually 4, 5, and 6 are all up there on Canvas, okay? If the graphical stuff is not working for you, if it doesn't make a lot of sense, I'm not forcing you to do it. I think it's pretty slick. I think it's pretty nice, but if it doesn't work for you and you really want the equations, they're at the top left-hand corner of your green equation sheet. We haven't really looked at them yet. So I would strongly recommend that you take a look at that video that's an introduction to the acceleration equations. It just walks you through. It's like 2 minutes, okay? You're not committing to lots and lots of time. 2 minutes of your life to learn those equations if you're going to do equations. And then if the equations are not supernatural, if they're not a natural thing for you to do but you want to learn more about them, there's a nice little 2.5-minute video about how to pick the right one. Because unlike the last unit, we've got more than one equation. We've got 4 that we're playing with a lot now, okay? And then there are 4 practice problems that I want you to work. These are all in the textbook, okay? There are videos on Canvas that walk you through both graphical and equation-based solving for them, okay? So you can watch each of those. This is the homework that I'm expecting that you have done as well, okay? You've got lots of physics to do. This is all up on Canvas as well. And just an FYI that we are going to quiz on Friday over this material. Okay, we are going to quiz on Friday over this material. So you have about 20 minutes right now to do physics. If you would like to move so that you can work with someone, that's fine. If you would like to borrow some headphones, they're over behind Ethan. You're welcome to do that. This is your time to do physics, okay? I'm also going to call some small groups out to talk, but besides that, it is up to you, all right? Do physics, friends.